everyone. Good morning. What an adventure today. Um, my name is Saikat, and I'm a PhD student at Department of ECE, working with Professor Jaideep Kulkarni, focusing on emerging memory devices research. Today's topic of presentation is on STT-MRAM, which has drawn a lot of attention in the last level cache applications. And the metrics that we aim for in this kind of applications is the density. It has to be very fast and low power. So we are going to talk about all of them, how STT-MRAM can achieve these metrics. We have, like Professor Incorvia has covered a lot about the concepts of STT-MRAM in class, and also we have learned a lot from Dr. Sousa's lecture. But I will just touch up a bit on this. So we have three layers, a barrier layer sandwiched between two ferromagnetic layers. And when we have those ferromagnetic layers in parallel state, their magnetization is parallel, we have pretty good band matching, which enhances tunneling between through the barrier, and we see a very low resistance. And when they're in the anti-parallel state, we see poor band matching and the tunneling is low, so we see a high resistance state. And this happens due to the spin conservation while tunneling. The upspin electrons will only tunnel if they see band states in majority spin, upspin, majority empty. And we know about the magical MGO tunneling barrier. It provides a very high MR. Experimentally, it's around 600%. And also very high spin polarization because of the delta one symmetry states present in the material, which cope up very well with the Coffee B layer. So to write in this memory, we use spin transfer torque from if we apply current along this barrier, across this barrier. So the current gets, the electrons get spin polarized in the pinned layer, and it tunnels through the MGO barrier while conserving its spin, and it provides some torque on the free layer magnetization, and that helps to realign the free layer magnetization in the direction of the pinned layer. Okay, and lastly, we have to use a transistor to source the current and sense the current while reading. And the biggest advantage of this STT-MRAM memory is this is BUL compatible. It can be integrated in the backend of line process, and that allows the cell density to be 6F square, where F is the minimum picture size. Okay, so this is a long table which compares different kind of memories, all established and emerging. But I want to bring your attention to the comparison of the SRAM and STT-MRAM, because in cache memory applications, it's the SRAM that it's competing with. So if you see the cell area, it's almost 10 to 15x lower. That gives us high density. And if you see the endurance, which is greater than 10 to the power 15, that is very good. It's non-volatile, which makes it like it doesn't draw any static power when it's not in active use, whereas SRAM draws like 20 to 30% write power while not actively in use. Okay, but despite all these advantages, we have very low, um, very high latency, which is like 10x compared to SRAM, whereas it takes 1 nanosecond to write and read, whereas STT-MRAM takes around 10 nanoseconds. So, and this happens um, because of the trade-off between the switching current and the speed of switching. Okay, we'll go more into that. So the takeaway is we need to lower the switching current as well as increase the speed to really compete with the cache memories. So I'll talk about a very interesting work which came out from IBM. So here they basically use two barrier layers, one in the bottom and one in the top. Okay, so the idea is to add up the spin transfer torque from both these layers into this free layer. And to do that, we need anti-parallel alignments of these reference layers, because if you see, like, current is entering the free layer from the top RL while leaving the free layer to enter into the bottom RL. Like, so the current, so the torque sign is different with the two barriers. So in this case, we need anti-parallel alignments of the reference layers. And if we do that, we see that the magnetoresistance gets affected, because it's like two anti-parallel layers acting against each other. So if you look at this plot here, these are the four distinct resistive states we see. And this is the RH loop. Now, let's say that the bottom layer has a high coercivity, so let's fix that in this alignment. And the free layer and top layer, top reference layer can switch in the process. So if we increase the field, we see let's start from 3, all are parallel, so we see a low resistance state. And then as we increase the field, the free layer switches, and that gives us a high resistance state. And then again, we go back to 1, where the top reference layer also switches. We see this resistance state, and when we reverse the perpendicular field, we see again this free layer switches back. We see a high resistance state, and then it goes back to 3 again. Okay, so we have 4 distinct resistive states, but we see here we can get higher TMR. Okay, number 4, where two reference layers are in parallel. But in number 2, we see low TMR, where two layers are in anti-parallel. But in this case, here, if they are in parallel configuration, we see the critical voltage to switch is around 0.6 volts. Whereas if they are in anti-parallel configuration, we see the critical voltage to switch reduces rapidly to 0.27 volts. So this gives us confidence that to increase the STT efficiency, we need the reference layers to be in anti-parallel state. Okay. So and that reduces the MR. So there is a trade-off between this STT efficiency and MR. Because if we have to increase the efficiency, the MGO thickness has to be high, and if the MGO thickness is high, the RA is high, and we see MR gets affected more. So this is another interesting work came out of IBM. Here they just replace the top barrier layer with a non-magnetic spacer. So this gives us like very low resistance. So the MR is not affected by this layer at all. Okay, the MR is only affected by the only MGO barrier that is there, but also the spacer layer provides the necessary spin torque, which increases the STT efficiency. So that's the idea. They didn't disclose the material, but most probably it might be ruthenium. And so if you see the IC RA plot, so RA is basically the resistance area product, which relates to the thickness of the MGO barrier. You see that compared to the single magnetic tunnel junction, in the dual spin torque magnetic tunnel junction, we see a 2x reduction of the switching current. So this is a comparison of all the configurations that we have here. The single MTJ is here, like high IC and high MR. Okay. Now, if we replace with dual MTJ, because the MR gets affected, MR is lower, even though we see a reduction in IC. So to increase MR, we need to lower the resistance area product of the barrier, where we again lose the STT efficiency. But with the DSMTJ, the green one, you can actually achieve the STT efficiency while maintaining the magnetic resistance. This is just a plot to show that the switching voltage is actually reducing to X from the SMTJ to the DSMTJ. And you can operate this at lower pulse width as well. So this is a right error rate versus switching voltage plot. So we all know that the right voltage increases or right current increases if we want to switch it faster. That's what is happening here. And more on this is available on this slide. So this plot looks like fireworks, but what is it telling us is that the current density has to increase rapidly if we want to reduce the switching time. Okay, and this is a plot where 50% switching probability is calculated. It's found experimentally with respect to the pulse width. So you can see the current density, switching current density is going up rapidly with reducing pulse widths. Here, like you can do some material optimization. So like if you use the free layer material 1 or 2 in different regime. So if we have like pulse widths greater than 10 nanoseconds, the thermal switching may help. So in that case, if you see this FL1 provides lower switching current. However, when we go below 10 nanosecond regime, we see both of them are rapidly increased as expected, but FL2 provides lower switching current. So material optimization is on the cards here. Yeah, so I'll just, Kaiho will cover, I think, on SOT. So this is just a comparison to show that this can really compete with SOT, and it can actually consume lower write power and lower current compared to SOT in sub-nanosecond switching regime. And in summary, so we have like STT-MRAM, which is really competent to replace SRAM because of its zero static power, 15x greater than density compared to SRAM, and very good endurance. However, it's not as fast. We still need improvement on write current because of the dynamic power consumption. So I have discussed two solutions came out of IBM, the DMTJ, where switching current can be reduced, but MR gets severely affected, and the DSMTJ can improve the scenario without any impact on the PMR. And they have also shown that sub-nanosecond switching is possible at the cost of large write currents.
Thank you.